Yes.
Okay. So today we're going to be talking about binary lifting, also known as binary jumping, and it's commonly used for various algorithms such as the LCA problem and for algorithms like heavy light decomposition. So before we get started, there's a few definitions that we're going to need to know. So a tree is a graph that has n nodes connected by n-1 edges, such that there's exactly one simple path between every pair of nodes. And we can typically root a tree, right? So we can just like take this one node and call it the root of the tree. And but once we've rooted it, we can call the parent of a node the direct predecessor of a node in a rooted tree. So basically the first node on the path from any given node to the root of the tree. And an ancestor is basically any of the predecessors of a node in a rooted tree, or all the nodes on the simple path from a given node to the tree's root. And then the LCA, or lowest common ancestor, is basically the node with the greatest depth that is an ancestor of two given nodes. So if we take this tree on the left, right, and we can just say it's rooted at node, we can say that it's rooted at node 0, right? So let's consider node 6 down here, right? Its parent would be node 2, because it's the node like right above it. And then its ancestors would be node 0 and node 2, because these are the two nodes on the path from node 6 to the root 0. 0 and 2. So if we then take a look at node 1, its parent would be node 0, because it's the parent like node above it. And then node 0 would also be its only ancestor. So if we were to process like nodes 1 and node 6, and we wanted to find the LCA, then the LCA of nodes 1 and node 6 would be node 0, because it's like the only ancestor in this graph. So similarly, the lowest common ancestor of nodes 5 and node 6 would be node 2, because node 2 is an ancestor of both of them, and it's the lowest one. The other common ancestor would be node 0, but node 2 is the lowest common ancestor. So how can we find this LCA? So one method of finding the lowest common ancestor of two nodes x and y would to be perform a DFS going up the tree from nodes x and y. So we can start by finding the depth of node x and the depth of node y. And then without loss of generality, let's say that node x has a greater depth than node y, right? So if we were here, right, and we wanted to find the LCA of nodes 1 and node 5, node 1 has a higher depth. Is higher on the tree, and node 5 is lower on the tree. So then we can just move up the tree from node x until we get to a node of the same depth as node y. So what that means is, since we're considering nodes 1 and node 5, we're going to move up the tree from node 5 until we get to the same height as node 1, right? So node 1 has a depth of 1, and if we move up the tree from node 5 until we get to a depth of 1, we would get to node 2, right? So then from there, we can just move both of our nodes up the tree one at a time until they reach the same node, and that common node will be their LCA. So here we're at node 1 and node 2, and then from both of them, we could just move up the tree once, and then we would get to node 0, which is their LCA. So this is a quick illustration. So if you wanted to find the LCA of nodes 1 and 6, so we can keep 2 pointers at the 2 nodes that we're currently looking at. So we want to find the LCA of node 5 and node 2. The depth of node 5 is 2, and the depth of node 1 is 1. And basically, since node 5 is the one with the greater depth, right, it's lower on the tree, the first thing we would do is we would go up the tree from node 5 until we get to a node of the same depth as node 1, right? So here we just go up the tree once, and now we're at nodes 1 and 2, which have the same depth. So now we can just make each of our pointers go up the tree one at a time until they reach the same node, right? So here they would just have to move up the tree once, and then we would get to node 0, which is our LCA. So we can say that the LCA of nodes 1 and 5 is node 0. And this is basically just some code that does it. So if the depth of B is greater than the depth of A, then we'll just swap them because we want to fix the node that has a greater depth. And so basically, once we fix that node A has a greater depth, we're going to keep going up the tree from node A until we get to a node that has the same depth as node B, right? So now that nodes A and B have the same depth, we can just go up the tree one at a time, right? So A goes to its parent and B goes to its parent. And then once A and B are like the same node, then we will have reached our LCA. So then we can just return it. So this code works, right? It runs an O of n time per query. And that's pretty good if we need to find the LCA once. But a lot of the time, we're going to want to find the LCA a lot of times. For example, if n is 1e5 and we want to find the LCA of some pairs of nodes 10 to the power of 5 times, then we would have nearly 10 to the power of 10 operations, which is very, very slow. So we can use this thing called binary lifting. And basically, we'll be able to find the LCA of 2 nodes in logarithmic time with a bit of pre-processing. So basically, binary lifting is a dynamic programming approach that we can apply to this LCA problem. And basically, our DP will work such that DP of node X for some number D will store the 2 to the dth parent of X. And so that might be kind of confusing, but I'll go more in depth later. So basically, values of X can range from 0 to n because they're just all the nodes. And because we're storing the 2 to the dth parent, and our max depth of a tree with n nodes is n minus 1, the maximum value of D would just be log base 2 of n. So the first thing that we're going to do is we're going to find DP of x0 for every node using one DFS. Because basically, DP of x0 just stores the 2 to the 0th parent. In other words, just the first parent of each node. And then during this DFS, we'll also find the depth of each node, which will be useful later. And so that might be kind of confusing, but I'll explain. So first, let's kind of like go over what these DP states mean, right? So we have a graph on the left, right? And it's basically rooted at node 1. So let's take a look at node 6. The first parent of node 6, right, down here, is just node 5. So we can say that DP of 6, 0 is 5, because 2 to the power 0 is 1, right? So similarly, the second parent of node 6, right, 1, 2, is node 4. And since 2 to the power of 1 is 2, we can say that DP of 6, 1 stores the second parent of node 6, which is node 4. So DP of 6, 2 should store the 2 squared parent, or the fourth parent of node 6, right? So 1, 2, 3, 4, which gives us 2, right? So DP of 6, 2 is equal to 2. DP of 6, 3 would correspond to node 6's 8th parent, right? So 1, 2, 3, 4, 5. And then there's nothing else, right? So this doesn't exist. So that's basically what the DP values for node 6 will store. If we take a look at node 5, the first parent is node 4. So DP of 5, 0 is 4. The second parent of node 5 is node 3. So DP of 5, 1 is 3. And then the fourth parent, 1, 2, 3, 4, of node 5 is equal to node 1. So DP of 5, 2 is 1. And then if we take a look at node 4, the first parent of node 4 is 3, so DP of 4, 0 is 3. And the second parent of node 4 is 2, right? So DP of 4, 1 is equal to 2. So does anyone have any questions on this part, like what the DP stores? Okay, cool. So how do we calculate these values, right? Because we're going to need to find a quick way to find the DP values. So notice that the 2 to the first parent of node 6 is node 4, and the 2 to the squared power of node 6, 1, 2, 3, 4, is node 2. Now, if you notice that the second parent of node 4 is also 2, right? So that may seem like a coincidence, but it's actually not. So basically what that means is to find the second parent of node 6, we need to move up the tree twice from node 6, right? And that would put us at node 4. And then to find the second parent of node 4, we would have to move up the tree another 2 times from node 4, landing us at node 2. So in this whole process, going from 6 to 4 and then to 2, we basically just move up the tree 4 times from node 6, right? Because this is 2 to the power of 1 moves. And then this is another 2 to the power of 1 moves. So then in total, we just made 2 squared moves. And this basically gives us the following relationship, right? The 2 to the dth parent of node I is equal to the 2 to the d minus 1th parent of the 2 to the d minus 1th parent of node I. And basically, if we go back to the example we just used, that means that the 2 squared parent of node 6, which is node 2, this is equal to the 2 to the first parent of the 2 to the first parent of node 6, which is equal to the 2 to the first parent of node 4, which is equal to node 2. And basically, if we were to express that in code, we would basically have the dp of id is equal to dp of id minus 1 of d minus 1. So some code, right? So this is just some code that runs a simple DFS, and this would basically tell us the depth and parents of each node. So here I'm setting LCA I0 of each node to P because it's just the parent, right? 2 to the power of 0 is 1. So LCA of I0 is just the node's parent. And then here we just go through an adjacency list from node V. And then if this node that we're visiting is not the parent, then we will update the depth of that node accordingly and then call DFS from that node. And now node I is the parent of that node. And then this is just some code to kind of initiate our LCA stuff, right? So this just fills out our DP states, right? It fills out the DP table. We just go from the depth is equal to 1 until our maximum depth, and then we just go through all of our nodes. And then this is basically the occurrence that we found earlier, right? LC of ID is equal to the 2 to the d minus 1th parent of the 2 to the d minus 1th parent of node I. So once we've done all of that, we're set up to actually do the LCA finding part of the algorithm. So we can use these DP states to find the LCA in logarithmic time. And we're basically going to use the exact same approach that we had used earlier. So without loss of generality, we can say that node X is lower than node Y. And then we'll just move the X pointer up the tree until it gets to the same depth as node Y. From there, we can move both the pointers up the tree until they get to the same node. And this is basically the exact same thing that we did in our linear solution. The only difference is that previously we had to move each pointer up 1 at a time. But using binary lifting, because we know the 2 to the power of 5th parent of a node, right? We can move a pointer up more than 1 node at a time. So this is kind of hard to illustrate on PowerPoint, so I'm just gonna draw this out, right? So the first step would be to move node X up until it gets to node Y, right? So to illustrate this, I'll kind of just make a very simple tree, right? Okay, and let's say we wanted to find the LCA of these 2 red nodes, right? Actually, I'll add a node. Okay, So the first thing that we need to do is we need to run a DFS. And then in this DFS, we basically just find the depth of each node, right? So I'll call this node the root, right? So then this will have a depth of 0. And then we can just go down the tree and assign depths accordingly. Right? So this node has this node has a depth of 3, and this node has a depth of 8, right? So the first thing that we want to do is we want to move our lower node up the tree, right? Until we get to a node of the same depth as our higher node, right? So basically that just means that we want to move this node up the tree until we get to a depth of 3. So previously, we would have just kept moving the node up the tree until we reach this depth, right? So first we go here, and then 7, this is a depth of 7, but we want to get to a depth of 3, so we keep going. And then 6 is too big, 5 is too big, 4 is too big. And then finally, we get to a node of depth 3. And this is basically the depth that we were looking for. We were trying to get to a node of depth 3. So here, we did a lot of jumps, right? We did like 1, 2, 3, 4, 5 jumps to get here. And if our tree is like, has a height of like 10 to the power 5, then that's like a lot of jumps. So basically, we can use our DP values to help find this. Once we have the depth of our two nodes, right? Like we know this is a depth of 3 and this is a depth of 8. We know how many jumps that we're going to make, right? It's just 8 minus 3 jumps is equal to 5, right? But in our DP states, in our DP values, right? We already know what the fourth parent of node 8 is, right? Fourth parent of node 8. We already know what this value is. So instead of doing these like 1, 2, 3, 4 jumps, right? We can just go into our DP array and then just make this in one huge jump. And then make this other jump, right? So that's 1 and then 2. So that's how we're gonna like skip over nodes and just use our DP. So another question arises, right? How do we know how big we should make our jumps? Well, to use this, we're gonna kind of express this number in binary, right? We know that we need to make 5 jumps. So we can express this in binary, and this is equal to 101 in base 2. So basically what this tells us is that in order to make 5 jumps, we need to make a jump of size 2 to the 0 plus a jump of size 2 to the power of 2, right? And we know how to do this, right? Our DP state tells us what the 2 squared parent of a node is. It also tells us what the 2 to the 0th parent of a node is. So we can just kind of like go through all of our depths and then see if it's one of the jumps that we need to make. And we can do that with like bitwise operators, right? So yeah, this is 5, so it's just 101. So we need to make a jump of size 4 and a jump of size 1. So we can just start by making our jump of size 4 and then our jump of size 1. And basically by doing this, as you probably noticed and as I probably said, we cut down on the jumps a lot, right? Instead of making 5 jumps, we only need to make 2 jumps. And this basically helps a lot, especially when we're dealing with like really big numbers, right? If a tree had a height, if we need to make a jump of height of size like 2 to the power of like 20, right? If we were to make 1 jump at a time, that would be super slow. But using binary lifting, we can just do this in 1 jump, which is very nice. So does anyone have any questions on like how to get a node to the same depth as the other node? Okay, cool. So once we've done that, we can proceed on to the next step. So I'll draw another tree down here. And your tree doesn't have to be a binary tree. I'm just drawing it as a binary tree because it's like easier to draw. Okay, cool. So now let's say, once again, we want to find the LCA of these two red nodes. So we know their depths, right? This is depth 0, this is depth. This is depth 0, this is depth 1, 2, 3, 4, 5, right? So we already know how to get this, the red node on the of depth 5 to depth 3, right? We can do 5 minus 3, and this gives us 2, which then turns into 1, 0, base 2. So this just tells us that we just need to make one jump of size 2. So we just make one jump, and boom, we're here. So once we're here, we can move on to the next step, right? Which is basically, we have two nodes that are on the same depth, and we just want to go up the tree one at a time until we would have gone up the tree one at a time until we got to the LCA. But this time, we're not going to do that because we have this DP thing that we can use to go a lot faster. So I'm actually going to add a node to this tree. Right, 1, 2, 3. Yeah, I'll add a node to this tree really quickly. And you'll see why in a second. Okay, and yeah. So this is depth 0, this is depth 1, this is depth 2, this is depth 3, this is depth 4, depth 5, and depth 6. So basically, now comes the question, how do we know how much to jump, right? Previously, we just looked at the difference between the two depths, turned it into binary, and that's how we knew how to jump. But here, we don't know what the depth of our LCA is, so we can't do that. So instead, what we're going to do is we're going to loop all the way from our max depth. Oh, this is bad handwriting, but it should be legible, to a like jump of size 0. So like a maximum size jump to a minimum size jump, right? Max jump to a min jump. Okay, so the height of this tree, well, not accounting this, like the height of the tree is 6, right? So the maximum size jump that we could really consider is a size of jump 2 to the power of 2. So let's consider a jump of size 2 to the power of 2. And basically what that means is we're going to take both of our nodes and we're going to jump a height of 4 from both of them, right? So if we were to jump a height of 4 from this green node, we would get to here. If we were to jump a height 4 from this blue node, we would get to here. And basically those values are actually the same, right? We would get to the same node. So if we made a jump of size 4, we would get to the same node. To the same node, right? So what do we do here? Well, the fourth parent of both of them is the same node. So this node has to be either the LCA of the two nodes or a node above the LCA of the two nodes, right? Here, if we just look at the graph, the LCA is obviously, there's no more colors. The LCA is obviously this yellow node, right? And we got to this node up here, which is above the yellow node. But we don't know that this is above the LCA, right? We don't know if this is the LCA or if this is a node above the LCA. Because if we made a jump of size 3, we would still get to the same node. And this would be the LCA, but we wouldn't be able to know that, right? Like we don't know that that's the LCA. So to avoid this kind of like situation where you don't know if it's the LCA or not, we're basically just gonna completely avoid this situation. If we take a size of jump 2 to the power of d, and it makes both of our nodes the same node, then we're just not going to make this jump. We're just going to completely ignore it, right? This is a bad jump. We're not going to make it. So what does that mean? That means that if the 2 to the dth jump is a different node, we will make the jump, right? So that might be kind of confusing. So I'll kind of go over it. So right now we're at our 2 red nodes. We're at the green node and the blue node. This green node and this blue node. So we're gonna go from our max jump to our minimum jump. So our maximum jump is a jump of size 4, right? So if we made a jump of size 4, as we covered here, we would get to the same node, which is bad. So we're not gonna make this jump. This is a bad jump. So our next jump size is a jump of size 2. So where would a jump of size 2 bring our nodes? Well, this green node would go up 1, 2, and we would get here. The blue node would go up 1, 2, and then we would get here. And then these nodes are different, right? They're different nodes. So this is a good node. This is a good jump. We can make this jump. Good. This is a good jump. So we're gonna make this jump. So after we make the jump, our nodes basically like change where they are, right? So now we don't care about these 2 red nodes. Now our pointers are at the green one and the blue one. Okay, so now we can go do our next jump size. What's our next jump size? Our next jump size is a jump of size 1. So if we jumped 1 from the green node, we would get here. If we jumped 1 from the blue node, we would get here, right? And this is once again the same node. So this is a bad jump. We're not going to make this jump. This was also a bad jump. So we're not going to make this jump. And then what's our next jump size? Well, we don't have another jump size. 1 was our smallest jump size, right? So this means that we've made all the jumps that we can, right? We can't make any more jumps. So that basically means we're done, right? Except we're not, because our pointers evidently are not pointing at the same node. However, you can notice that the parent of either one of these nodes will be the LCA, because the only way we would get to this situation is if the first parent was, if a jump of size 1 would bring the nodes to the same node, and they're currently not on the same node, then like the parents of either one of the nodes would be the LCA, if that makes sense. Yeah. Basically, if like once we finish all of our jump sizes and our nodes are where they are, the LCA is just the parent of either one of them. So yeah, once we do that, we basically found our LCA, and then we can just return the value. So does anyone have any questions? Okay, cool. So yeah, now we can go over some code. So this is in C++, but it's like basically the same thing as the code in Java. It's just like there's no swap method built into Java. So the first thing we're going to do is we're going to want to get to our nodes to the same depth. So to start off, once again, we'll just fix the node that has a greater depth. And then we just loop through all of our possible depths. And if we can make this jump and it wouldn't like go higher than the other depth, then we just make the jump. When I was drawing it, I talked about like checking, like finding the binary representation of the difference of the 2 nodes. But this also works because it does like the same thing. So once we've done that, we can actually find the LCA because they're both on the same height. So we're going to loop through all of our values of D. And if this is a valid jump, right? Like if this jump would bring us to two different nodes, then we can just update our nodes, right? X is now equal to the 2 to the dth parent of X, and Y is now equal to the 2 to the dth parent of Y. And then once we've done all of our jumping, we get to step 3, which is the final step, which is just to return the LCA. So if X and Y are different, then that means that the LCA is just the parents of either one of them. So then we can just set either node to its parent. I just chose to set X to its parent, and then we just return X. So the only case where like X and Y would be the same node is if the starting node Y was the LCA. And basically what I mean by that is like, if we go back here and we wanted to find the LCA of this node and this node, right? The first thing we would do is we would bring this node up to depth 1, and that would get us here. So our 2 pointers would already point to the same node. So in that case, like we're already at our LCA. So we don't need to do this thingy. So yeah, after you do that, you can just return it. So I decided to cover binary lifting through the lowest common ancestor problem because it's like probably the most commonly used application. We can also use it to do other things, like we can find the sum over a path in a tree. It's used in heavy light decomposition. You can like find the state of a graph after it's like shuffled X times. Like if you have n nodes and they're shuffled in like the exact same way, and you want to find the state after shuffled like k times, you can use binary lifting to do that. And then there's like many, many more applications of binary lifting. It's kind of hard to describe like the exact situation where you would use binary lifting. So these are some practice problems that you can do to like refine your skills. And then these are some other resources. There's like the USICO guide, CP algorithms, a Codeforces blog, and a YouTube video. So we still have quite a lot of time. So I'll be going over the first practice problem, Planet Queries 1. Yeah. Let me see if I can send it. I'm not sure how to send it into the chat, but if you search up CSES Planet Queries 1, you should be able to find it. So yeah, I'll just put it here and give you guys some time to read it.